Welcome to SPMM Revision on Demand. In this podcast, I will discuss the concepts of study design in clinical research. Clinical research has three basic goals. Number one, to measure the frequency or severity of a problem. Number two, to study the relationship between two variables, for example, cause and effect, or risk factor and disease, etc. Number three, interfere with the physiological or pathological process and assess the results. Based on these three goals, we can classify research studies into three types: descriptive, analytical, and experimental. Descriptive studies are useful to describe the status of a few people or a population. The common types of descriptive studies are case studies, case series, and cross-sectional surveys. Analytical studies aim to analyze the relationship between two or more variables. For example, between a risk factor such as cannabis and the development of a disorder such as psychosis. There are three types of analytical studies: ecological study, case control study, and cohort study. We will see these subtypes in more detail in the later part of this video. In experimental studies, we manipulate one or more variables and note the effect on the others. For example, we alter prescribed medications and assess the reduction in symptom burden in a group of patients. The three types of experimental trials include uncontrolled trial and the two types of controlled trials, non-randomized and randomized controlled trial. You will hear more of these in due course. Both descriptive and analytical studies are called observational studies, as no active intervention is carried out in these studies. In contrast, experimental studies are termed as interventional studies. Let us now discuss descriptive studies. Case reports and case series are descriptive studies that describe a problem observed in a single or a small set of patients. The advantage is that these are cheaper and quicker to complete, though they do not provide any conclusive evidence. Cross-sectional surveys are the most common type of descriptive studies. In such surveys, all individuals are observed at a single time point. This design is very useful if one wants to study the distribution of one or more variables in a sample. For example, we can conduct a cross-sectional survey to establish the number of subjects with myopia and obesity in a town. Such surveys are also called prevalence studies, as they help establish the prevalence of a health problem. We can also measure incidence by using cross-sectional studies. Suppose I conduct a survey in my town this year and estimate the prevalence of myopia, and repeat the same survey next year as well in the same town. I can now deduct the number of extra cases or new cases of myopia in the last 1 year, and thus I can deduce the incidence rate of myopia by conducting two cross-sectional surveys. Cross-sectional surveys can also be used to investigate possible association between two variables. Cross-sectional studies allow us to collect data on one or more variables at any given time from a study population. If we collect the data on two variables, one being a risk factor and the other being a disease outcome, at the same time, we can estimate the association between these two variables by classifying the sample into one of the four cells: exposed and unwell, exposed and well, not exposed but unwell, not exposed and well. But any such association is only speculative. The assignment of cause and effect is arbitrary here, as no temporal relationship between these two variables could be inferred from a cross-sectional design. We now move on to analytical studies. To infer causation, we must first establish an association. This is the necessary first step, but not sufficient. How to establish association between two variables? Let us look at an example. I want to study if antidepressants are associated with increased rate of gastrointestinal bleeding. I have four possible options available to me. Firstly, I can choose a defined sample and collect data on both GI bleed and antidepressant use in the sample at a single time point. If GI bleed is more often seen in those taking antidepressants, we can then infer a high degree of co-occurrence and a putative association between these two factors. Secondly, there is some degree of natural variation in antidepressant prescription rates across the GP catchment areas in the country. I can obtain the reported rates of GI bleeding as well as the rates of antidepressant prescription from these GP catchment areas and see if a relationship exists between the two rates. I may find low rates of GI bleed in areas where the prescription rates of antidepressants are also low, suggesting an association between the two. Thirdly, I can define two groups: patients who have GI bleed, that is cases, and patients who do not have GI bleed, that is controls. I can then compare the amount of antidepressants taken by these two groups at some point in the past. Finally, I can select a group of people exposed to antidepressants and a group who had never taken them. I can follow these people for a period of time and see how many in each group develop gastrointestinal bleeding in due course. The first type of study is called as a cross-sectional survey. We have already seen how you can use this design to investigate putative associations. The second type of study is called as an ecological study. The third type of study is called as a case control study. And the fourth type described here is a cohort design. Let us see some more details of ecological design. In this graph, two variables are plotted. Suicide rates in a 15-year period in Denmark are plotted against antidepressant sale rates in the same time period in the same country. There seems to be a pattern suggesting a drop in suicide rates with an increase in antidepressant prescription across the years. With this data, can you conclude antidepressants reduce suicide rates? In other words, can you infer a causal relationship between the two variables? What we saw now is a group-level correlation. Within a defined population in Denmark, in the years when antidepressant prescription was higher, the suicide rates were lower. This data cannot tell us whether those who committed suicide really took antidepressants or not. In other words, we can only make group level, not individual level inferences from this data. The error of making causal associations on the basis of an ecological observation is called as ecological fallacy. This error is unique to ecological studies. Now, let us see the design of a case control study. In a case control study, you always start with two naturally occurring groups: those who have the disease, that is cases, and those who do not have the disease, that is controls. You then investigate these groups to determine how many were exposed to the risk factor of interest in each group. At the end, you will get four cells: cases who are exposed, cases who are not exposed, controls who are exposed, controls who are not exposed. 2 points to remember in a case control design. Both exposure and disease have already occurred, so the study design is always retrospective. Also remember, in a case control study, the investigation always starts from cases and controls. Before we see cohort studies, let us consider the definition of the term cohort. A cohort is a group of individuals who share something in common and are observed over a time period. For example, everyone on a case register may form a cohort. Everyone living in a specific region may form a cohort. The term birth cohort refers to individuals who share the year, decade, or time period of birth. Similarly, the term exposure cohort refers to individuals who share the exposure to a suspected risk factor or the causal agent for a disease. In cohort studies, the study population can be divided into two naturally occurring groups: the exposed cohort and the non-exposed cohort. We then investigate these groups to determine how many develop a specific outcome, for example, a disease, in due course. At the end, you will get 4 cells: exposed individuals who are diseased, exposed individuals who remain healthy, non-exposed individuals who are diseased, and non-exposed individuals who remain healthy. In a cohort study, there are 2 time points of interest: the time of exposure and the time of outcome. The time of outcome always occurs after the time of exposure. Hence, cohort studies are always longitudinal in design. A third time point of reference is when the research study begins. Using this reference time point, we can classify cohort studies to prospective and retrospective. If the time point of exposure is historical and the time point of outcome is in the future, this is called as a prospective design. If both these time points are historical, with reference to the starting point of the research study, that is, both exposure and outcome have already happened, then this is called a retrospective design. What is the difference from a case control study then? Note that the outcome in a retrospective cohort study still occurs only after the exposure, a distinction that cannot be made in case control designs. In other words, a retrospective cohort study is very similar to a prospective cohort except for the calendar time in which the data collection takes place. Note that you cannot conduct a retrospective cohort study if someone has not already collected the data on outcome and exposure in the past. So, a case registry or a database is essential for this purpose. In this slide, I have listed some differences between case control designs and cohort designs. Most of these are obvious. I want you to focus on the last point. If a disease is very infrequent, then a large number of exposed subjects must be followed up to observe even a single case to emerge. In this case, a cohort study can be expensive and even pointless. For rare diseases, case control studies are more useful. But if the exposure is rare, case control designs are not of much use. For example, terrorist attacks can cause PTSD, but terrorist attacks, fortunately, are very rare. If you study a group of 100 PTSD patients in your clinic, you will be lucky if you can see a single patient who was exposed to a terrorist attack. In this case, to study the effect of terrorism on PTSD, a cohort design will be a better option. Sometimes you can perform a case control study on the basis of data collected from a cohort study. As you know, in a cohort study, the study population can be divided into an exposed and a non-exposed cohort. If we follow them up, we can see 2 groups emerging from the exposed cohort. If we pick some individuals from both these groups and compare them, we are actually conducting a case control comparison. This case control design is now nested within a cohort study. This is called a nested case control study. Such studies are often possible when retrospective outcome data is available either from registers or from samples obtained from cohorts. In your exam, you often see nested case control studies developed from the General Practice Research Database, which is a primary care database available in the UK. The third major study type is the experimental study, commonly known as a clinical trial. Here, we do not just observe, but we actively interfere. We manipulate one or more variables and see what happens to the other variables of interest in due course. Often, the variable that is manipulated is the administration of a treatment agent, and we assess the response generated by the agent. In other words, we assess the relationship between 2 variables, one being the treatment and other the response observed on follow-up. If there is only one group of subjects, all of whom receive the active treatment, this is called an uncontrolled trial. If we have 2 groups, then this is called a controlled trial. If you randomize the subjects to decide who gets the active novel treatment and who gets the placebo or standard treatment, then you are conducting a randomized controlled trial. If you do not randomize the sample, you're conducting a non-randomized controlled trial. As shown in this flowchart, in a randomized controlled trial, the study population is randomly assigned to two groups. One will be exposed to placebo and the other exposed to active drug. We then follow up prospectively to see who develops the outcome of interest, that is, response to treatment. In this sense, a clinical trial is nothing but a sophisticated cohort study. The major difference is that the researcher actively intervenes and randomly allocates the sample to one of the two groups in a randomized controlled trial. Clinical drug trials can also be classified according to the stage of development of a drug. Phase 1 trials are small trials aimed at demonstrating the safety and dosing, usually in healthy volunteers. Phase 2 trials are conducted on patients, generally a small sample, to determine biological efficacy. Phase 3 is usually larger and a randomized controlled trial conducted to determine the incremental usefulness of a new drug compared to either placebo or an old established drug. Phase 4 studies are post-marketing surveillance studies to generate large-scale information. So far, we have seen the three major types of study designs. At this point, it will be useful to think about the various criteria that need to be satisfied before we can say an event A causes an outcome B. Epidemiologist Bradford Hill has laid out certain criteria that need to be satisfied before we can say A causes B. Among these criteria, one of the most important points is the issue of temporality. To say A causes B, A should occur before B occurs. We have seen how this claim cannot be made from cross-sectional and case-control studies, but can only be made from follow-up designs such as a cohort study or a randomized controlled trial. There are several other criteria shown here. I recommend you to revisit them when revising for your exams. That is the end of this podcast on basics of study designs. At this point, I want you to think of the following questions. Thank you for using the SPMM course for your revision.